Hello, everyone. I think we can start our next presentation. So we will have two presentations. The first one from Jari Kayhko and the second one from Angeliki Tzanakaki. Okay. So the first one will be the presentation of the using modeling to understand and improve industrial oxygen delignification process. Jari studied paper technology in Aalto University and made his doctoral thesis, The Resignation of Mechanical Pulp, in the La Peranta University of Technology. In 2003, Jari moved to Savonlinna, working as a professor, and started to build a new pulp and paper-oriented research unit called FIBRE Laboratory. Nowadays, Jari is concentrating to studies related to chemical pulping and specialized to oxygen delignification and the effect of gases in the process. So, Jari, the floor is yours.
Okay.
Thank you.
Thank you, Sofia, for your kind introduction. And ladies and gentlemen, I will speak you today about modeling of oxygen delignification process. And here's outline of my presentation. First, I will tell about the motive, why we are making these modeling studies. Then I will go through these modeling principles very shortly. Then I will tell you about material methods and laboratory and mill studies. Then I will go through these modeling results and at the end some discussion and conclusion. So I have to go first a little bit to history. So it was about 20 years ago that we founded a new laboratory to the little town called Savonlinna in Finland. So this is quite a big laboratory stuff and so on, and we have a very big pilot plant. So in this pilot plant we can test and study very, very big equipments used in pulp mills. And mainly we have been studying these chemical mixing processes. So we have a so-called MC loop where we can circulate MC pulp and the amount is very big. In this moment it's so big that it's 7,000 tons per day. So bigger than any existing pulp mill. So we can put there different big equipments, and Andrits has mainly tested the equipment, new equipments in there. But what we have in university side done, we have tried to study these mixing processes. So first of all, we tested and invented new ways to measure this mixedness. And one very important measurement what we invented was this continuous inline bubble size measurement. Yes. And now with this measurement we have been doing laboratory studies and mill studies, and we have get information that what is the oxygen bubble size in the oxygen delignification process. And very important step was that we are making cooperation with Adrian van Heiningen, and together we pronounce this new equation which says that what is the oxygen mass transfer in the process if we know the bubble size and the oxygen volume in the process. Okay. This means now that earlier this modeling was not possible because people didn't know what is the concentration of dissolved oxygen in the process, which is very, very important parameter in here. But through these studies, we now have a possibility to do that, and we have done it, and we are going further to learn is it really so things that we think they are. And one idea is also to now take new online measurements to the pulp industry. This one is this oxygen bubble size, and very interesting and potential measurement what we are doing now is also this measurement of residual gas oxygen concentration, because this gives a lot of information what there is happening in these big reactors. And final target is also then use this modeling in order to understand and improve these mill processes. So here you can see the all essential things related to this modeling. Seems a little bit complicated, but actually it's quite straightforward. And the main equation is here. Sorry. This one. So here we have this void of oxygen in the reactor, and here is a bubble size. And through these we can calculate this mass transfer coefficient, and from here we can calculate the mass transfer, and then we get this important information. What is the concentration of dissolved oxygen in the process? Then there is a lot of other things, but I won't go them no deeper. Maybe one thing it's very interesting in here. This is a diffusion coefficient of oxygen. As you can see, this number is very, very small. So now I have a question for you that if I have a tank of water, 1 meter, and we have in the bottom, we have the oxygen, not in the top, only in the bottom. So how long time it will take that this oxygen is diffused to the surface? Is it minutes, hours, weeks, hours, light hours, or what? Something, you say some number. Number, you say number. How many? Okay, and this is pretty difficult. It's nearly 1 year. So it's diffusion of oxygen is very, very slow process. And that's why we need really, really small bubbles there in the process. So this modeling is now this key point in here, and it's very nice indeed, so that we can get information from different sources, from literature. We get these values for these parameters. Then we can make these laboratory tests. We can predict that what the laboratory should happen, and then we can also get this laboratory data and set our parameters in there. And most important, then we can get from the mill the essential information for the modeling, and then we can model these processes and study, predict, optimize, reduce, or benchmark, whatever we like. And here is an example of this Excel sheet used for the modeling. So in this moment I'm using Excel. It's a very good tool for this. So I have a calculation in here, and I can put these parameters in here, change them, and put the mill information and so on, and then I can print this essential information what I need or what I am studying. And one most important most important here is this saturation level of oxygen in the reactor. So what does this mean? So it means that we have in certain pressure, certain temperature, certain maximum amount of oxygen which can be dissolved. And now we allow calculating this saturation level, that how close we are this maximum amount of dissolved oxygen. If the number is 1, then it's totally saturated, the process. So here you can see this, our measurement looks like this. We can use it in a laboratory, and when we make delignification in laboratory, we can see which kind of bubbles we form in there and how different things affect to this size of the bubbles. Then here is a system in the mill, and here is one mill where we have been doing these studies. So you can see this oxygen delignification process can be really big. So this reactor, its height from the ground is about 70 meters. So until this moment, we have been doing these studies in 8 different processes, 4 soft food process and 4 hardwood process. Then about And here is this information what we have got this from the mill and use this in the modeling. Don't go so far with this. But then about the results, about the soft food processes. So we have studied 4 different soft food processes, and we have noticed that the bubble size in these processes has been really, really small. And so when we have calculated now the saturation level, you can see in here, I don't know where I have this number of, okay, average bubble size, what is here. So if we have this 0.15, then we get very rapid saturation of the process. So these small bubbles are really, really good, and they produce very rapidly this saturation. And after this, we have now concentrated more to these hard food processes, since situation seems to be such that in these hard food processes, the bubble size is nearly 10 times higher compared to the soft food processes. So we have here one hard food process. There the bubbles are very small, but these others, it's quite big. And we have also now done laboratory studies and mill studies, and we have tried to clear it out that are these bubbles too big. And until this moment, we are quite certain that in this moment, in these 3 cases, they are too big. And here is one example. This is this birch bee process. So there we managed to change this bubble size so that they were feeding the deformer just before the reactor, which makes so that the bubbles were very big. So we shut down the deformer and we get much, much smaller bubble size. And then we also measured the amount of residual gas in the top of the reactor, and it went to the 0. So it means that then more oxygen was consumed, and in this case, these bubbles were too big. Okay, here we can see now these 4 different processes. So this first process, here we get a very good saturation, but these other 3 processes, they are not saturated. And also we have been doing mill studies so that how much this rotation speed of mixer affect, how it affects to this bubble size, and we know that it has a certain effect. And then we looked this EUCA B process, and we made the calculations, and we knew that in the second mixer, the rotation speed is 700 rounds per minute, and we calculated that if we could speed it up to 1,200, then we could decrease clearly the bubble size, and then we could get this process saturated, and also then when it's saturated, if you put a little bit more alkali, then you could really make a big change, improvement to this kappa reduction, about 0.7 units. And this is very interesting that we said to the mill that if you have any possibility to change the process, and they have now decided to change it, and in the next shutdown, they increase this rotation speed, not to 1,200, but 1,000. And it's really interesting now to see that does it help the process. Since these changes, making these changes in the process, it's quite difficult sometimes. Okay, then we come to these modeling results. So here in the up, we have these very important parameters. It's this parameter A, which says how rapidly this delignification occurs there in the process. And we get here some numbers, and you should not take these too seriously in this moment. There is a lot of different things which make some mistake, but after all, this looks very, very nice. And actually, we need to have more mills to model. So if you have any mill, and I can send you the list of information that I would need to have, and I can model, and then we could get more information. What is the situation in different mills? But in this moment, we are concentrating more to these things related to this oxygen, saturation level, and consumption. So here we can have these numbers, how much oxygen is consumed. And of course, there is in the literature also a lot of information how much this oxygen delignification should consume oxygen. But the problem is that the deviation is from 0.2 kilos to 2 kilos. So it's very big. We don't know exact, but these numbers seems very, very good and sensible. We can see that in soft food process, we don't need so much oxygen as in hard food process. Also, if we have 2 reactors, the second reactor is consuming more oxygen per kappa decrease unit. Okay, but then next steps, what we are looking, because we have had possibility to measure this amount of oxygen in this residual gas, we know exactly how much these processes are consumed oxygen, and then we can get these numbers. How much is consumed to lignin reactants, and then if they are using oxidized white liquor, how much is consumed to their total consumption, oxygen charge, and then we get this number, how much it seems that there is extra oxygen put to the process. Of course, we need a small amount in a distillate form, and in about 1 to 2 kilos, but these are very interesting processes now. It seems that they are using much more oxygen than needed. And we have done then studies in this mill, this EUCA B mill. We decreased the oxygen charge 5 kilos, and the modeling says that this should not have any effect on kappa reduction, and it didn't. Of course, we have a lot of deviation in here. It's not very certain, but we see that there didn't happen any major things. Also, another process, we made a few times this test, and we decreased the oxygen charge about 4 kilos, and there we didn't see any changes in the process. And also, now with the modeling, we can also calculate these kind of issues, that what is the optimal charge of oxygen in the process. And we can see that the shape of the curve is like this. So if we go too small oxygen charge, then the kappa reduction goes down very rapidly, or kappa increase. But if we put too much, then it goes also up, because it doesn't anymore help if you put too much oxygen. It only takes void in the reactor and shorten the retention time. And that's why if you put too much, then it will go up. Okay, yes. Here is one very interesting what we get from the modeling, that if you are using pure oxygen, then you can go in this residual oxygen amount to 0 and still have a saturated process. And this is important if you have some problems related to these residual gases. They might be worse in your washing and screening and so on. Okay, the conclusions then, this modeling, it's now started to be a useful tool to study these existing processes, and we get a lot of now information that how these different processes are working. Thank you very much.
So thank you very much, Jari. So we will move forward with Angeliki with the presentation of fiber liberation first pulping concept. So Angeliki is a motivated researcher working as a research scientist at VTT, specializing in biorefining process. Her academic background includes a master's degree in organic chemistry from the University of Crete, and the MMC Tech in biomass refining from Altri University. Since 2024, she has been pursuing a doctoral degree at Altri University. The floor is yours. Thank you.
Yes, thank you very much for the introduction. Hello, everyone. Sorry, I'm actually happy to be here today, and I would like to speak about my work in the project Fiber Liberation First Concept, a work that is, thank you, a work that is conducted in VTT in Finland and is also part of the emission-free pulping program that was introduced from my colleague yesterday, Kiran. So, to first make an introduction into the topic, as you already know, one of the biggest challenges nowadays is the high increase of the CO2 emissions and also the big energy demand. And the pulp and paper industry is among the most energy demanding and industries with a high share in the CO2 emissions that are produced globally. In the dominant kraft pulping process, 40 to 50% of the wood is only converted into pulp, and then, which means that 50 to 60% of wood is lost. And at the same time, the materials that from the incineration of dissolved wood components during the recovery of chemicals and energy, and in addition with the high complexity of those recovery systems, lead to an increase of the CO2 emissions. We believe that a high-yield pulping can enhance the efficient use of wood as raw material and also improve the environmental performance. And to reach our target on this work, we developed a new pulping concept where we aiming to have efficient use of wood biomass as material, minimize the biomass losses, and also simplify the recovery methodologies while maintaining the quality of the fibers produced. Our approach includes first engender fiber liberation by mechanical means in a disc refiner at high temperature, followed by a chemical treatment to partially delignify the fibers and then increase their bonding potential. In the first part of this work, we actually worked with spruce wood chips in a single disc high consistency refiner. And then we screened different refining conditions in order to find the optimum conditions that will allow the liberation of fiber as intact as possible and long fibers with limited fiber damage and amount of fines. Between the different parameters that were tested, we screened the refining pressure between 3 and 7 bars, the rotational speed from 2003 to 3000 RPM, and then the disc plate gap from 0.1 to 0.4 millimeters. Here you can see an example of the separated fibers that were derived from this step. And as you can see, we had when we were applying the suitable conditions, we could get quite intact and long fibers with a small amount of size and small damage. Here you can see a graph where we were able to get actually quite long fibers when we applied the wide blade gap and higher refining pressure. And also the energy consumption was low for these liberated fibers. We conducted in total almost 30 trials. And after this step, we continue to the oxygen delignification, which was used to partially delignify those fibers. Starting from the never dried liberated fibers, using sodium carbonate as the alkaline source, and 140 degrees and liquid to wood ratio around 10, we produced brown pulp, and we screened the oxygen charts and cooking time as different varied conditions to see the effect of those conditions in the quality of the pulp. As you can see here on these graphs, we were able to obtain high yield pulps, 67 to 80%, by using this methodology, with increasing viscosity from 450 to 470 mL to gram. And what we can observe from here is that the more we extend the cooking time and the more we increase the oxygen charge, the more the yield is and the kappa number are decreasing. To even verify those results, we conduct the chemical composition analysis on those trials, and we can see that lignin content is decreasing the more we cook. We extend the cooking time of the process, and xylan content is reduced in a low level. But what is interesting is that the glucomannan level is almost the same, and is independent on the cooking time. Then, when we did the same analysis for the oxygen charts, for the varied oxygen charts, we also see that the lignin content is decreasing, and again, the glucomannans are remaining on the same level as with the spruce chips, but only in the case of where we have no oxygen loaded on the system and only nitrogen. Then we see that actually lignin hasn't been reduced at all, and also decrease of glucomannans in that case. In addition, we performed another analysis where we want to see the distribution of lignin on the fibers and get some information of the process. We used the fibers, we embedded them in a resin, and then we got the cross-section of those fibers. And with using confocal laser scanning microscopy, we compared the untreated liberated fibers with the oxygen-treated fibers. What we can see from here is that we actually got, we see an intensity in the autofluorescence in the case of the oxygen-treated fibers. And as we know that the autofluorescence is a result of the lignin that is present on the fibers, then we can say that this shift in the higher wavelengths suggests that we have a modification of the lignin structure. Also, another observation here is that we see a change on the shape of the fibers in the case of the oxygen-treated fibers, and which means that we have a change in morphology. The penetration of oxygen, the penetration of fibers by oxygen is quite even, and leads in the collapse of the fibers in the case of the thin-walled fibers. In conclusion, we have developed a new pulping concept combining mechanical and chemical treatment in a novel way. We see that oxygen pulping is an environmentally friendly and chemically benign process that can improve the bonding potential of the liberated fibers, and then we can obtain high yield pulps with high hemicellulose content with that process. Yeah, I would like to thank also the research technicians for the help, and also the Business Finland and the Mission Free Pulping for all the funding that was provided. And here is my contact if you want to get in touch with me. And thank you.
Thank you very much, Angeliki. So we have time for a few short questions. Someone from the audience? Yes. Gabriel. And you.
Good morning. So Gabriel Souza from Altri Group. Thank you for a very nice presentation. Just curious, two questions regarding your work. In what way, so this is a new way of treating mechanically wood to produce pulp. So the first question is, in what way does this differentiate from the conventional mechanical processes or mechanical processes that already exist and existed in the past, and that for some reason or other have been declining in application? Second part of the question is, the properties of this pulp, what is the attractiveness of the pulp that you're producing in terms of paper applications? Because it's one way to produce it. The other way is to actually sell it on the market that will compete ultimately with the bleach chemical grades. So thank you. Two questions.
Yeah. Thank you for your question. Actually, in the first question, there is some literature that this concept, the oxygen pulping, while first liberating fibers, has been tested, but we revisit this concept because they suggested that the fibers, the first treatment actually, should be improved, and then we can have a very good properties on the second treatment. That's why we actually retry this concept. And also, we would like to, we know that the oxygen pulping is more environmentally friendly, and yeah, we would like to, I don't think we aim for paper applications, and this is a high yield pulp, so it still contains lignin. So, but in this project, we are not actually testing the applications. We are testing the fiber production and then the recovery, which is not presented here, but it will be part of this project. So the applications will be tested in further later project. I hope I answered your questions. Thank you.
We have here another question. Jari?
Do you know, do you have any number or idea how much oxygen is consumed in your process?
Thank you. I was actually expecting this question from you. Lately, we were also having this question. And at the first trials we collected the gases that were produced during the treatment, and then we found a way to calculate what is consumed, but it's not, unfortunately, it's not presented here because it was really the late days that we found out this. But I think that when we go to the higher oxygen charges, we see that oxygen is also actually consumed less compared to the medium oxygen charge. That's what I can say for the moment.
Yes, I just calculated it. It should be about 200 kilos per ton. Yes, and then you have a good question how to mix it. But it can be done.
I think we have time for another one.
Hi, Luis Machado from Reis, and a question for Jari. I think I understood from your presentation that in the pulp mills you had a much higher bubble size, and it was related with the foamer application before the oxygen delignification. And the question goes, after this conclusion, did the mills resync the foaming addition? And because it seems simple to address and tackle this problem, although of course we have a lot of different extractives and many foam problems in that area. How did the mills react to these results, and it was possible or not to correct this?
Okay, very good question. Actually, the situation is such that in this mill where we made these tests, the situation has been changed, and they have now enough small bubbles. They don't need to, but there is some things that they should do. And then we have tested this also in another mill, and it has had no effect on the bubble size. So this is an area which we don't know yet very well. So that sometimes it might be, it's affecting the bubbles and sometimes not, but we don't know why and so on. But clearly there is possibly, and of course this bubble size measurement, what we are using, we are now using it also to optimize these deformer additions.
So I think we don't have time for more questions. So once again, thank you very much for your nice presentation.